All right, stat students. So I don't have like a official lesson for you in this video, but I wanted to go through and sort of reiterate some points with the lessons that we've already covered, particularly when we learned what a sampling distribution is. This chapter is actually especially challenging for distance learners because usually when I teach it, there is more hands-on activities that are being done. So the next video, you will be able to participate in one of those activities kind of at your own pace at home. But I need to do it in person before I'm able to bring it to you guys because I want to go ahead and get some data for it. So what we're going to be doing in this video is looking at the problem set. So go ahead and have that handy either on Delta Math. So go ahead and pull up your Delta Math on the side to work these problems, or if you have your version that is printed, you can have that as well. Or you can just go to Delta Math and look at the questions. Okay. So we're going to start by looking at numbers 6, 9, and 10. Okay, 6, 9, and 10. So I'm going to what I want to do with this is I'm going to give you some hints to what the answer should be. I'm going to write this out to the side over here. So for one answer should be a sample distribution. One answer should be a population distribution. And then one answer should be a sampling distribution. And I think through process of elimination, if you're looking at this through my video here, you should be able to I think one of these does not have these as an option. Let me actually change the font to, let's make it white. Okay, and let's bold it. There we go. So these are the possible answers over here on the right side. And we're working 6, 9, and 10. That's what we want to look at. Okay, so I'm going to pause and you can use Delta Math. Remember, you get 3 attempts on each one. So if you want to take 2 attempts per question, go for it. But I want to make sure that we understand the differences between these 3 terms right here. And remember, this chapter is based on sampling distributions. Okay, so I'm going to pause it. I want you to go on there, try to answer 6, try to answer 9, try to answer 10. If you miss them twice, then go ahead and hit play on the video because then I'm going to explain each problem. Okay. All right. So hopefully you've had time to answer those. Maybe you got them right. That'd be awesome if you did. But we're going to go ahead and talk about these. So number 6 here, it says, I flip a coin 10 times and record the proportion of heads I obtained. Then I repeat this process of flipping the coin 10 times and record the proportion of heads obtained. And here's a keyword: many times. Okay. When done, I make a histogram of my results. This histogram approximates what? Well, if you remember the guy that had a very Coach Harris-esque voice screaming, and he's talking about sampling distributions, right? And he talks about proportions. I think he used the idea, percent of people are sexy and they know it, right? Well, this is the same concept, right? This is a sampling distribution. The key word is I take many samples of the same size. So that's where we get sampling distribution. And that's the idea behind a sampling distribution, is many times. Okay. All right. Hopefully that helps clear up maybe the definition there for you about what these distributions actually are. Let's look at number 9, the distribution of values for all members of a population. Okay. So this is all members of a population. Well, that is going to be the population distribution of the variable. Okay, this is C. If I have all the data, then I'm going to know what that distribution looks like. That wasn't the case with the pennies, where we found average age, because we don't know the population distribution of that. It's not like and it's almost impossible to obtain all that data. Right? I mean, there's just too many pennies. We looked at the Reese's Pieces candy machine, and I actually know what the population looks like because 45% are orange. But still, I don't have all of that data. It's not really possible. So on the next lesson's video, we actually are going to have the population distribution. So you'll be able to connect this definition a little bit better. And then, but that is all the data of the population. And then from the population, we take a sample. And if we were doing a sampling distribution, we'd do like number 6, we'd take repeated samples, repeated samples, repeated samples. Also, by the way, the fact that they use a histogram does not matter. It doesn't matter if the sampling distribution is a histogram, a dot plot, a box and whisker plot. So here was our data from class. Here's the dot plot. We could easily change this to a histogram. All I have to do is type it in my calculator and just change the data to histogram, but it just so happens it was easier to make a dot plot, okay? So that's what we did there, okay? Answering number 10. Number 10, the distribution of values from a single sample, this is important, single sample of size n from a population. Well, we've kind of process of elimination. We got population, sampling. So this is a sample distribution. This is one sample. Okay, and this is the distribution of sample data. That's all that is. Now, is that what we have here? No. This is many samples. This is the samples all the same size 5 from each sample that the students took that make a sampling distribution. So this is a sampling distribution. All right. This is not a sample distribution. All right, it's not one sample that has all its data distributed. This is many samples that are going on here. So that is, understanding that is pretty much the most important idea in this chapter. So we have those, okay? Next, we are going to look at, we're going to talk about, let me go back here. Let's talk about the variability of a statistic, okay? This is the spread of the data, right? This is how spread out the data is. Okay, the spread is determined mainly by the size of the random sample. So larger samples give smaller spreads. Then we have spread of the sampling distribution does not depend much on the size of the population as long as the population is at least 10 times larger than the sample. Let me move my camera over here. Variability is represented by the standard deviation. So your standard deviation, we've always said that, right? It is the spread of the data. Larger sample sizes produce smaller spread. Okay, so we're going to be looking at a few questions here. We're going to be doing 15, 16, and you can work 17, but we're not going to. 15, 16, and we want 12. Okay, so 15, 16, and 12. Let me actually go ahead and copy this one in here and we'll write that up. So top right here, you're going to be working these questions 15, 16, and 12 in your notes or in your problem sets. Okay, so let's go ahead and do that. I'm going to pause the video. You'll see the numbers at the top right of my screen. You can go in on Delta Math and work those. That's fine. But 15, 16, and 17. Okay, so you had time to work those. 15 is just the definition. It is just the definition. How do we reduce variability of estimates from a simple random sample? You should use a larger sample. That is our definition. That's what we put. That's what's in here, right? Larger sample, smaller standard deviation. Larger samples, smaller spread. That's how we deal with that. That's the rule. Okay. So let's look at number 16. So it says if we took an SRS of 1,700 people from California that has a population of 34 million, an SRS of 1,000 people from Detroit, population 1 million, which sampling distribution would have a smaller standard deviation? Okay, so this problem tries to intimidate you with the population size, but if we go back to our description here, it says the spread of the sampling distribution does not depend much on the size of the population as long as the population is at least 10 times larger than the sample. So we're still going off this rule that larger samples give smaller spread, or larger samples mean smaller standard deviation. Okay? So with that in mind, the best choice on here is C because California has a larger sample size. All right? It doesn't have anything to do with population size in this case. Okay? It's all about the sample size that reduces spread. All right, so let's go and we're going to look at number 12. Oh, and we can also do number 7. Number 7, variability of a statistic is described by the spread of the sampling distribution. So 7 is A on this one. That's just a definition. But let's look at what we did for 12. We have dot plots of values taken by 3 statistics and 30 samples from the same population. This is very similar to what we did with the pennies. There's 3 distributions here for that, okay? So number 12, the statistic that has the lowest variability. So what we're looking for is the smallest spread, okay? Well, we can see looking at statistic A, it is the most spread out. So it's probably not that one, so it can't be A. Then we compare B and C. Are one of them less spread out is what I mean, better than the other? Well, if you look at it, one of them shifted, but both of them are about the same amount of spread. I'd say the standard deviations are pretty much the same. So really the best choice for this is E, because it says B and C have similar variability, and it is less than the variability of A. That is the most true statement of all of these, okay? So that is the most true statement, okay? All right, cool. So we're through those. Now we're going to talk about the last idea that was in that first section, which is the idea of an unbiased estimator. A statistic is used to estimate a parameter. A statistic used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution is equal to the true value of the parameter being estimated, okay? So we're going to start with, I'm actually just going to go ahead and work this one with you guys, okay? We're going to start with number 11, and then we'll talk about some other questions as well, but this one I'm actually going to work. So notice here it says the true value of the population parameter is marked with an arrow. So what if I do this? I'm going to draw a vertical line in red straight up from this one. That's not very good. Hold on. Boom. It's better. All right, and that red line represents the true parameter. And our definition, what it's saying is the mean of the sampling distribution. So all 3 of these charts, of these graphs, the center of A, is it on the red line? The center of B, is it on the red line? And the center of C, is it on the red line? That's what we're asking. So considering this, the one that has the most bias, because that's what it wants, the statistic that has the largest bias is the one that is not centered on that red line. Well, which one is that? Well, that's C. C is sort of shifted over. Its actual center is probably more about here. And this is what we call bias, when the sampling distribution is not actually lined up. So maybe they sampled incorrectly. There's a lot of ways that bias can be created in a sample, but that is a visual for what bias would be. I tried to explain this with our penny example. So we said imagine, because I drew all these blue lines on here, so we said imagine if the red line was the true mean for all pennies. Well, there would be bias created with my top one because it's not lined up perfectly, okay? But let's say that the green line was actually the parameter. Well, that means all of them were biased. And we said, well, that might make sense because my population wasn't or what I was sampling from wasn't representative. The samples weren't necessarily random. There weren't any 2020 pennies available in the samples that were being done by students. So, that's possible sources of bias, okay? Also, we did come to find out that these dots that Evan did, he said that he messed those up and he was going to recalculate them, okay? So that's the main idea here. Now, let's look at number 13. It says, based on the performance of the 3 statistics in many samples, which is preferred as an estimate of the parameter? So which sampling distribution is the best? Well, we want the one that is the least bias and the least spread. Both of those are important for these distributions, okay? Well, based on our answers to 11 and 12, so by the way, 11 was C, has the highest bias. Based on 11 and 12, B is going to be the best estimate, okay? Statistic B is going to be the best estimate. So you have other questions. You should be able to answer the first 17 questions for whatever's left in there for the first 17 questions. You should be good to go on those now. You should also be able to answer all the way through 30 based on the last lesson we did as well. And then tomorrow I'll be putting out another video, and we should be able to answer the remaining questions on the problem set. We're going through this chapter. It's actually shorter than I remember it being, but we're doing a pretty good job going through these. If you have any questions about particular problems, please reach out to me.